talking about, I developed that just to check that, by a Sannett curve on a dot plot to see if these probes are working at all. Yeah.
Mm-hmm.
Yeah.
Yeah. Cause you've got a biotin on there, right?
Exactly. See, you knew, you already reading the mind. But on the record, I'm not supposed to say, and on the record, you guess.
Okay.
I think the technique was
for sure.
Yes.
So I'm interested, if we think about, you're working with these custom oligonucleotide pools as a whole, what are your biggest pain points or like annoyances with them?
One of the for us, the challenge was in the beginning was designing, investing so much money, and we did not know if some of the probes are gonna even work.
Mm-hmm.
And so, we designed it again. It's purely based on, bioinformatics, yes, statistics that it'll bind, but then again, how it works in a tube, we don't know. That was a challenge. The other thing is, the footprinting procedure itself is, it's nerve-wracking, right? If you think about it, you're dealing with a 30-mer sequence that is protected. So a ribosome spans around 30 nucleotides on an mRNA. Mm-hmm. And you're essentially, dealing with a 30 nucleotide RNA sequence, later on converting your DNA. And there's no way to check if how these probes behave. You have to wait for a couple of days to complete the other steps and then see, oh yeah, let's look at this. And when I say let's look at this, we cannot check the probe efficiency on a gel by polyacrylamide gel. It's only the NGS that is being done, and that's a lot of money being spent, right? So if there was a way to kind of figure out, not the dot plot, but if there was a way to figure out in the RiboSeq itself how the probes were doing, that would have been nice. But then again, this is not my specific problem. I think this is a research community problem, is that it's hard. What you have asked is a very important and a very valid question. Mm-hmm. It's hard to answer.
Yeah. That makes sense.
Yeah.
Okay. So is there anything about your workflow with oligos that I didn't get into that you think is important to understand?
Mm-hmm. Let me think. So I'm kind of, you can hear me. I'm going to talk to myself just to make sure that I have
For sure.
given you all the information. So the good things, I'm just thinking about right now, the list of good things was that, the price, turnaround time, and the tech rep, that was really good for us. That worked out perfect. I'm really happy with that. The painful points were designing these probes, not a lot of resource available, specifically in our case. In mammalian systems, we don't have any idea. And the other thing is, I would say checking the efficiency of the probes was another problem for us. If I remember right, that's something that we had discussion. So we spent a lot of money. The MySeq was essentially that $7-8 that got spent was essentially just to purely check the efficiency and the promiscuity, and specificity of the probe. Now let me think if I'm forgetting anything. So. I don't think so. I'm forgetting anything. I mean, these probes are divided, they come in, again, this information may be not important, but, when we ordered the probe, it came in a tube rack, 64 different tubes, individual tubes. I had to make, I think this is a good information, right? It's that they came all in 64 tubes. Again, different probes, say example for 18S, is not required at the same, whatever nanomoles or picomoles concentration as any other probe, right? Are you following what I'm trying to say?
So you didn't need the same concentration of one probe as another probe.
Yes. So, just sitting down and calibrating that, the first time was I'm interesting in a very science way. I'm not going to say challenging, interesting. That's the positive spin in it. That took, I would say 48 hours, 72 hours just to think about it, to make the right molar concentration. And again, we were riding in the dark, right? I have no idea it's going to work or not. So, that was a challenge. Again, there is no way to assess that. It was just a first shot. And whatever the NGS result told us, that was very extremely valuable to go back and help in make the master mix again. So, combining all the oligos and having a master mix. And that's something, another information to use, that when I made these probes, I had added an equimolar concentration for all the 64 probes and made a master mix that I used to store in the -20. And I would use that to do an X dilution to make whatever concentration I needed. Now, after the first NGS, I remember that I had to go back and get to the -80 and remake my master mix based on the concentrations that we found that, okay, this might be the best concentration for, say, probe 10 or probe 30 or something like that. So, that's something that step was done for each and every time. And ultimately, I think we reached to a stage, like I said, we had hit that Vmax point. There was no difference. So that master mix stays as it is. Other than that, I think I've given you all the information.
So I have two questions about that.
Yes.
One is there a reason why having an overload of any of the probes would be problematic, or just from a cost perspective?
You are asking really, really tough questions. And the reason, I'll tell you why that question is so, again, important, is that you're adding overloading of probes. It's a very good analytical chemistry question. You're titrating, right? That's the idea here. So if you start titration, if you have other probes in too much quantity, are you providing enough time for the reaction to reach the saturation? That meaning that there are other, whatever millions of reads, right? Millions of contamination reads. Are we providing enough time, or adding probe number 10, which is not even required at that quantity, and the probe number 12 that was supposed to bind did not get a chance to do that? So that's the question. I think you're trying to get a very good biochemistry question. And to answer that, the first time when we did this experiment, like I said, I used equimolar concentration. I had no idea. We just did this by, pure statistics and the bioinformatics results that were there, that yes, 18S will be the most prominent one. Let's bump up the level, as opposed to 5S rRNA, which is, not as compared to the 28S or 80. So those kind of phase, just I would say calibrations were already done, programmed into this. Later on, once we got the NGS data, that's where we started tweaking the concentrations to answer your question properly.
So it makes it a more efficient reaction.
Yes, exactly. That's how I would put it. Yes.
And then the other one is, you said you had to go through several MiSeq chips, to check everything. Is that because you had to run something and then check and then run something and check again? Or did you actually need all the lanes on each MiSeq chip? Or if you had access to a HiSeq, could it have just done one run?
Oh, if I had access to the HiSeq, okay, there are two reasons to that. In my specific, well, let me answer that question. Yes, if there was a HiSeq available and there were multiple lanes, again, depending upon the price, the cost would come into play. Here, what happened in my specific case is that I had applied for an internal grant, and I got the grant. So I had some money. My PI was happy. I said, you know what, we are not worried about the reads per se. We were doing this. So on the side, when I said we were testing our probes, we were actually doing our experiments also. So when we send out the sample, right, we would multiplex it. We'll mix the samples, and because these are barcoded, right? So we'll barcode the libraries and we'll mix it. So, MiSeq, it was, rather than giving us 2 21 million, which is supposed to be, we were not getting that much. It was very poor number of million of reads. And that's not the problem with the probes. It was the problem with the kit that we were using. And that's also, we figured it out what to do with it. So now, even with the MySeq, we can